So speaking of magnetic fields, we actually are able to see auroras on Saturn, which are areas where the magnetic field is arcing back into the planet at the north and south magnetic poles. And charged particles from the sun actually follow those magnetic field lines and crash into the planet and give up their energy in the form of visible radiation. So that's what we call the aurora borealis on Earth. It's really exactly the same effect, and we actually witnessed that on Saturn as well. Because this is a false color image that actually shows a little more dramatically the color variations, but we actually can see the shear motions, and we can see that the shear motions drive storms, just like what we saw when we looked at Jupiter. This is a plot of the velocity of the wind at the surface of Saturn as a function of latitude relative to the average. And what we find is that at the equator, we see a strong eastward motion of the clouds, that's eastward spin relative to the average. But we see much lower velocities and actually even contrasting velocities between different bands. So that's, again, driving this differential shear flow that I was talking about before. And by the way, this is the zero line right here. So relative to the average, we actually see some motion in a contrary direction relative to the average motion. Very similar to what we see when we look at Jupiter. And in fact, Jupiter's great red spot is driven by the strong shear between these two layers. The upper layer is negative relative to the average, and the lower layer is positive relative to the average. So this is giving us this winding up of the great red spot on Jupiter. And we're seeing a similar effect on Saturn, but it's not quite as dramatic in some ways because, well, let's see, the strongest excursions are around a few hundred kilometers per hour. And yeah, it's pretty comparable. We're seeing about a few hundred kilometers per hour excursions from the mean in the case of Jupiter as well. So both these planets have atmospheric circulations that are reflecting the same basic phenomenon of vertical convection combined with a strong Coriolis effect. So the strong Coriolis effect actually does give us an equatorial bulge in the case of Saturn and Jupiter, because both planets have spin periods of about 10 hours. The tilts of Saturn and Jupiter are a little bit different. Jupiter has sort of very little tilt, only about 3 degrees of tilt. Saturn's is in the mid-20 degrees. So we're going to see, in a sense, stronger seasonal variation on Saturn. Okay, so moving on to Saturn's atmosphere. Now, we already talked about Jupiter's atmosphere. Jupiter's atmosphere was like 95% hydrogen, or 85% hydrogen. We're seeing 92% hydrogen in the case of Saturn. Okay, so it's interesting to contrast these because they're both giant gaseous planets, which form in the cold outer part of our solar system and probably formed from the same primordial material, meaning the same amount of hydrogen and helium. All right, so when we look at these numbers, I should point out that this is the composition measured at the cloud tops. Now, we don't have any way to drill down into Saturn or Jupiter and know what's going on deep inside. So when we're talking about atmospheric composition, what we really mean by that is the cloud top composition. So when we look spectroscopically at the cloud tops on Jupiter and Saturn, we don't see the same thing. We actually see a little more hydrogen in the cloud tops of helium of Saturn than we do in the cloud tops of Jupiter. And we see less helium in the cloud tops of Saturn compared to what we see in the case of Jupiter. Most of the trace elements are pretty much the same. So like Jupiter, Saturn was cold enough to retain its primary atmosphere. That's why we're seeing all this hydrogen. The terrestrials lose their hydrogen because they're so close to the sun, they're hot, and they have low mass, so the hydrogen escapes. These bodies are much more massive, and out of the cold outer solar system, the gas velocities are low. So the gas actually doesn't escape. So this is really the main reason that we're seeing the transition from the terrestrials to a completely different class of planets. Because it's so cold out there that the escape velocity is lower. The escape velocity from the planet is higher than the actual velocity of the hydrogen gas moving around at that temperature. Now, it's exactly the opposite with the terrestrials. The escape velocity is lower and the hydrogen gas velocity is higher, so that it just evaporates and leaves. But for the Jovian planets, the gaseous planets, it's exactly the opposite relationship. Very high escape velocity because of high planetary mass, low gas velocity because it's cold, and so you actually find the hydrogen gas maintained. The primary atmosphere is actually maintained. Well, the two planets probably started out with very similar atmospheric composition, so we're still facing a puzzle here as to why the cloud top compositions are a bit different from each other. Sorry. Okay, so again, if they have the same composition, why then do we see different actual compositions when we measure the cloud top abundances of hydrogen and helium? Well, we believe that, as I mentioned, Jupiter has a more massive rockier core versus Saturn because, again, we're seeing a higher density in the case of Jupiter than we're seeing in the case of Saturn. That might have something to do with this phenomenon. We can also look at a cross-cut of Saturn's atmosphere compared to Jupiter's to get a little bit more information. The zero on these plots is at the cloud tops. Because remember, there's no solid surface, so we index the zero to the cloud tops. And what we find when we compare Saturn with Jupiter, first of all, let's look at the temperatures. The cloud top temperature right there on Saturn is actually below 100 kelvins. That's even colder than the cloud top temperature on Jupiter, which is 125 kelvins. All right, so that, on the face of it, is obviously just because Saturn's farther out from the sun. Solar heating is weaker, so you're going to expect a lower atmospheric temperature. At the lower temperatures in Saturn's atmosphere, you actually see different types of ices. We see ammonia ice. There's also deeper layers of ammonium hydrosulfide, some water. Now, we did see ammonium hydrosulfide, and water ice in the case of Jupiter as well. But notice that the difference here is that these vertical scales are not actually exactly the same. The distance from the ammonia ice layer down to the water ice layer, in the case of Saturn, is around 300 kilometers, 200 or 300 kilometers. On Jupiter, the distance from the ammonia ice layer down to the water ice layer is less than 100 kilometers, only about 75 kilometers. So we think that the compression of the atmosphere that we're seeing in the case of Jupiter, compared to the more vertically extended atmosphere that we see for Saturn, actually explains why we see a very bland-looking Saturn. Because you see, if we wanted to look past the ammonia layer and see a nice blue watery stripe in the atmosphere, well, you've got to look down around 200 kilometers to do that. To see the water layer in Jupiter's atmosphere, we only have to look down around 75 kilometers. So we think that there just really aren't many gaps in the atmosphere that allow us to see farther down to that deeper layer, in the case of Saturn. The deeper altitude we need to look to see the water ice, it just isn't possible because the clouds tend to obscure that. All right, so this is sort of an operational explanation for why we're seeing less color variation when we look at Saturn. But you could then ask the next question, which is, okay, well, why? Why is the atmosphere more vertically extended in the case of Saturn than in the case of Jupiter, right? I mean, I'm sort of presenting this to you as an explanation for why the atmosphere looks sort of plain and yellowish on Saturn, but, you know, why do we have this more extended layer in the case of Saturn than in the case of Jupiter? Well, it brings us to a discussion of the surface gravity. We look at the surface gravity. We say surface gravity, but we're really talking about the cloud top gravity when we're talking about the gaseous planets. So let's just do a quick calculation. The standard here is the Earth, 9.8 meters per second squared, gravitational acceleration at the surface. The Moon's is much lower than that. When we look at Jupiter's, we get 24.9 meters per second squared. So if I were floating above Jupiter and I drop my laser pointer, which the battery just fell out of, do that. Anyway, for every second that an object falls, it's going to gain almost 25 meters per second of velocity. We look at Saturn, 10.38 meters per second squared, actually very comparable to Earth's surface acceleration. So the bottom line here is that the acceleration due to gravity around Jupiter is about 2.5 times stronger than the acceleration due to gravity around Saturn. And this is just because Jupiter is much more massive. It's about 3 times more massive. You're seeing a ratio of almost 3 right there, basically reflecting the 3-to-1 ratio of the masses. All right, so this has something to do with the extension of the atmosphere that we were talking about.